services in India. They come from a university and the industry collaboration. Go ahead, Gauri. We can see the video first.
I am presenting the concept of using speech analysis for deriving breathing patterns and use them to identify respiratory tract problems such as COVID-19. Traditionally, chest and abdominal belts are used for capturing breathing patterns that are uncomfortable to wear for longer periods. Hence, we propose a novel non-intrusive mechanism of extracting breathing patterns from speech signals and use them to monitor the physiological, psychological, and cognitive health of individuals. This paper focuses on the detection of COVID-19 from speech-derived breathing patterns. Using the dataset from the breathing sub-challenge of the INTERSPEECH Compare 2020 challenge of 49 speakers' speech and breathing signals captured simultaneously. We built a regression model that can extract breathing patterns from speech signals called as Breathing Pattern Encoder. Further, the DiCOVA Track 1 dataset has cough and Track 2 has speech and breathing audio samples. We apply this encoder model to the DiCOVA challenge audio samples and represent the cough, speech, and breathing signals with their respective breathing patterns. These breathing patterns are then used as feature vectors by the decoder module and fed to the COVID-19 classifier for the detection of COVID-19 status. Uncovering the encoder and decoder blocks. The speech signal represented with 27 features is fed to the encoder. It comprises of 2 bi-LSTMs followed by LSTM, then a bi-LSTM and again a LSTM layer. The node of each layer are as shown in the brackets. The output dense layer has damage activation. The loss function calculates the Pearson correlation loss. It has a skip connection after first 3 layers. Batch size of 250 frames corresponds to 10 seconds of speech data. We submitted the challenge results using Decoder 1 architecture. Later we did some modifications and got the Decoder 2 architecture, which gave better results on the development partition. Decoder 1 comprises a dense layer with 250 nodes and sigmoid activation followed by an attention and LSTM layer, each with a single node. The output layer provides COVID-19 status using sigmoid activation. In Decoder 2, the input layer has a leaky halo activation function. It has an additional 1D convolution layer in between 2 attention layers. Each layer follows with the LSTM layer having 32, 16 and 8 nodes respectively. COVID-19 positive samples feature vector average is a query for the first attention layer. Again, the last output layer has a sigmoid activation function. Results are as presented here for track 1. The evaluation set results are submitted using MFCC and breathing features with Decoder 1. Breathing features are giving more than 9% improvement in AUC in the detection of COVID-19. On the validation set, breathing features alone with Decoder 2 have given 57.4% AUC in the detection of COVID-19. An improvement of around 4% is observed when both MFCCs and breathing features are used together. For track 2, breathing features perform the same as that of MFCCs for counting data and perform better than MFCCs for vowel E data. However, perform poorer for breathing audio data. The feature set comprising of both MFCCs and breathing features are performing the best throughout, with a maximum AUC of 68% on validation and 67% on the evaluation set of breathing signals respectively. Thank you.
Thank you. That's really interesting. Let me remind everybody that you can ask questions by clicking on the question mark icon on the right-hand side of your screen. We don't currently have any questions for Gauri there. Let me ask, you went into some detail about the encoder and the classifiers for this challenge, but you didn't really say anything, I think, about how the breathing features were calculated. You mentioned that it was using the Compare 2020 data set. Can you say a little bit about how you calculated the breathing features using that pre-training data?
The breathing features are actually entirely time domain features, and we have used a combination of 10 time domain difference features along with ZCR and autocorrelation. So all of them are actually time domain features.
Oh, so it's really just 12 features, it sounds like.
Yeah.
Wow, that's remarkable. And those were designed by hand in order to perform well on the breathing challenge. And so
yes.
you adapted them to this challenge.
Yes.
That's really neat. Thank you. And you saw an advantage by combining those together with the MFCC.
Yes, a combination performs much better than both MFCC alone as well as the time domain alone.
Thank you. There's a question from the audience. Biaozheng says, what is the definition of breath pattern and how many have you found so far?
Breathe pattern, it is a representation of speech signal in terms of corresponding breathe values for a duration, for fixed duration, which is 10 seconds in our case.
Sriram asks, can you help understand why breathing features did not perform as well on the breathing task in track 2?
Yeah, so the encoder is trained with the speech signal basically. So we have used the features extracted from speech signals and have applied them on cough, breathing, and speech, that is vowels. So that can be a probable reason of them not performing well on breathing.
All right, thank you. If there are no more questions, maybe we should then go on to the next talker. Thank you very much.
Thank you.